concluded. We'll invite Daniel. It's a great pleasure to introduce Daniel Glasscock. We'll speak on sums and intersections of multiplicatively invariant sets in the integers. Thanks, Dan. Go ahead.
All right. Thank you very much for the opportunity to speak. I actually spoke 1 year ago on Zoom here at this conference on this topic. And I feel like it could have happened that I just spent the last year on one long Zoom meeting. It possibly could have just happened. I'm not sure. My mind is blank. Anyways, I hope that I say enough new things for people that heard this talk last year. I don't know if anyone has had the pleasure, like I have many times, of finishing a paper and then understanding what you wrote, and then having to go back and, anyways. Okay, so today I'm going to tell you about sums and intersections of multiplicatively invariant sets in the integers. And we're going to talk about intersections in sum sets. At this point, maybe I don't need to define a sum set. The multiplicative structure we'll consider for these sets is structure that is described in base R or base S representations of integers, okay? And the basic heuristic that we have is that if A and B are structured with respect to multiplicatively independent bases, so for example, 4 and 7, then these two sets are somehow independent. So what independent means can change. And so I don't know why my keyboard is not advancing the slides, but I can click. We have a couple of motivating conjectures to keep in mind here, some conjectures that are close to what I want to talk about. The first is this conjecture by Erdős, 1979, which says that for all n greater than or equal to 9, the ternary expansion of 2 to the n should contain at least 1 2. Now, the real conjecture here is that the base 3 expansion of the number 2 to the n should really contain all of the digits 0, 1, and 2 as soon as n is large enough. And the way that I think about this is that 2 to the n is very easy to write down in base 2. So 2 to the n in base 2, of course, is just 1 followed by a bunch of zeros. That's a very simple expansion. And so in base 3, it somehow can't be that simple. In base 3, we ought to realize the complexity. And so in base 3, by realizing complexity, in this case, I just mean that at least one digit 2 shows up. The best result so far as I'm aware, is by Ligarius a decade ago. And he says that this happens, and the conjecture holds for lots of n's. Okay, for most n, in fact, this holds. But we still don't have the finiteness of this conjecture. The finiteness meaning finitely many exceptions. And there's a related conjecture which has a very similar flavor, that sort of folklore that says that there are exactly 3 numbers, 0, 1, and 82,000, whose base 2, 3, 4, and 5 expansions use only the digits 0 and 1. Again, this is just a conjecture. The best that I know of is a recent work of Burrell and Yu, who showed that that the set of numbers whose base 2, 3, 4, and 5 expansions only use the digits 0 and 1 is pretty small. And I'll have a little bit more to say about this in just a few minutes. In a longer version of this talk, I would go into talk about some of the sort of context for these types of conjectures. There are some much older related conjectures and results for real numbers. So all the way back to Ramanujan, Mahler, Steinhaus, and then much later, say in the 60s, Furstenberg and others. And so they're not always just about sets, but they usually have this type of flavor. So for example, if we take 2 numbers which are multiplicatively independent, say 2 distinct primes, and we consider structure with respect to one of those numbers and structure with respect to the others of those numbers, then the structure is somehow orthogonal. Okay, so I'll say a little bit more about reals in just a few minutes. These are the conjectures to keep in mind to help motivate our talk. Something that appears in both of these conjectures is a set which has a Cantor set. It's a set with a restriction on the digits allowed in a certain base. And so we're going to introduce some terminology for that. we're going to call those P Cantor sets. This is the analog of Cantor's middle third set in the integers. If you've taken a first class in real analysis, you've met Cantor's middle third set, and here is the sort of analog, natural analog of the integers, which is just all of those integers in base 3, which are written with 0 and 2 only. You can write it out in decimal. It doesn't have a very particularly nice form in decimal, but of course, in ternary, this would look a lot simpler. If you want to try and draw a picture of this, or you want to have an idea of what this is, when I say P Cantor, you should think this is a sparse set. Okay, so up to n, there are n to the log 2 over log 3 many elements. And this is correct up to a constant. I think it's like 1 and 2. It varies between constants 1 and 2 up to that many elements. Okay, log 2 over log 3 is the dimension of Cantor's middle third set. Okay, so now we're just going to do the same exact thing now with letters instead of numbers. So P Cantor set is a set of the form CPD. There, it's all of those integers which are written in base P using this set of allowed digits. D can be what you'd like. Okay, this has a dimension, log cardinality of D over log P. And this for us is just going to mean that the number of elements in this P Cantor set is n to the dimension, roughly speaking, on the first n integers. Okay. So we're going to fix two distinct primes. Those are going to be our multiplicatively independent integers. And we're going to fix a P Cantor set A and a Q Cantor set B. And we're going to ask, to what degree are these sets independent? This is sort of what those motivating conjectures we're grabbing at. And I'm going to offer you answers in 3 different directions. So simultaneous structure. Is it possible to have both P Cantor structure and Q Cantor structure simultaneously in the same set? Notion of geometric or probabilistic independence, and a notion of additive combinatorial independence between these sets. So let's start with the simultaneous structure one. If A is contained in B, that is, if our P Cantor set is contained in our Q Cantor set, then either our P Cantor set is trivial or our Q Cantor set is trivial. But there's just no way to have a P Cantor set contained in a Q Cantor set. So in other words, if you try to write Cantor's middle third set in base 17, you'd need all 17 digits. Okay, this is actually not so hard. I think if you get bored during my talk, you could prove this. So this is, I'm going to talk about how these generalize in a few minutes, and maybe the generalization isn't as easy, but this one, I think if you play around with this, you'll get a good feeling for it. It is not possible to have simultaneous structure in this sense. The corollary there would say that the only set which is both P Cantor and Q Cantor at the same time is the trivial set, and so the set containing 0 and all non-negative integers. Here's how one way you can think about how to prove something like that. And again, this is all I want to say about the proof. A 25-minute talk is not so long. If you take any word that might appear in base R, so just take any word in the letters 0 up to R minus 1, there's an arc on the circle with a property that for any real number x that's large enough, the fractional part of log x over log R falls within that arc, tells you that the floor of x as an integer begins with that word w in base R. So there's an arc on the circle which sort of tells you that number, the floor of x, will begin with a specific word in base R. So if you're looking for that word, it's enough to make log x over log R fall within this arc. And now you might get a feeling if R, I realize I've gone to an R when I should have made it a P. I apologize for that. R equals P. You're going to need to use somehow Q in this formulation as well, right? Q and P are distinct primes. Somehow here in this formulation, log Q over log P being irrational is going to matter. Things start rotating on this circle. And of course, log Q over log P being irrational will tell you that a rotation by that angle will equidistribute, and we'll fall into that arc quite often. Okay. Now we're going to go on to the second point, that geometric or probabilistic independence. So to do that, let's look at just a finite chunk of our set. Remember, A is a p-Cantor set, B is a q-Cantor set. We'll just look at the first finite pieces of these sets, the interval 0 to n-1. And we could ask, is it true that if we treat these as random events, that they're independent? Right? Maybe it happens that selecting an element, for example, at random from A and knowing about that element, it doesn't tell us really anything about whether the element is in B or not. Well, okay, this almost could be true, maybe, but we actually have examples where the intersection is empty, even though A and B are quite large. So this is another exercise. Can you find a p-Cantor set and a q-Cantor set, which are quite large? They use a lot of digits, but actually they don't intersect. There are congruence obstructions that you can bake in by choosing the right digits. And if you bake in the right congruence obstructions, you might get an empty intersection. And so really all we're going to ask about here is an inequality. So is this inequality possible? And the answer is yes, we can show that this inequality is possible up to a factor of n to the epsilon. So I hope that I have time at the end of my talk to go through a bunch of open questions, which are really tantalizing. And the extent to which this is true is still an open question. But at least up to a factor of epsilon, let me tell you what we can say. This is what our theorem says. If the sum of the dimensions of our Cantor sets is greater than or equal to 1, then we have that inequality that I just put there, but I have to multiply the right-hand side by an n to the epsilon. So I'm losing a power in n. If the sum of the dimensions, on the other hand, is less than 1, then in fact, the intersection is very small. I can't say that it's finite. I can't say that it's empty, but I can say that it's less than, in cardinality, it's less than n to the epsilon. Now the quantifiers read like this: for all epsilon, for all sufficiently large n. So what I would say is that A intersect B here has 0 dimension. That in fact, A intersect B is a set, which could be infinite. I can't rule that out, but at least it's pretty small in this sense. And when we apply that to one of the conjectures that I had mentioned in the beginning of my talk, we get this result, which is actually a result of Burrell and Yu, but follows from our more general theorem here, that if you look at those integers which are written in base 0 and 1, sorry, base 4 using digits 0 and 1, and in base 5 having digits 0 and 1, then that's pretty small. There aren't many integers like that. Now, right, what do I want to say about this? Oh, right. The reason for this is that log 2 over log 4 plus log 2 over log 5 is just less than 1. So in fact, we're in this second case when we apply the theorem. Okay, so this is a probabilistic independence type of statement, and I called it geometric because if you introduce a notion of dimension, then this has a flavor of geometry rather than probability, and there would be time to do that in a longer talk. But if anyone asks, maybe at the end of the talk, I can explain. Let's talk about some sets. If, again, A is a p-Cantor set and B is a q-Cantor set, and we add them together, and they're additively independent, we hope that there aren't a lot of coincidences amongst the sums. And that can be measured by asking, is AN plus BN in cardinality about as big as it can be? How big could it be? Well, remember AN and BN are both contained to this initial interval 0 to n. And so AN plus BN can't be much larger than n, right, like 2n. But it also can't be much larger than the product of those sets just by trivial upper bound. And so we're going to ask for the lower bound. Can we get that? And the answer is yes. So again, this result here has a very familiar flavor from the previous one. So for all epsilon, for all sufficiently large n, the sum set an plus bn. So we're adding elements whose base p expansion only uses some digits to integers whose base q expansion only uses some digits. And we're saying that there aren't many coincidences amongst those sums. And again, here we lose a power, so it's divided by n to the epsilon. And again, there's an open question here that's very nice and very natural and has a parallel open question in the real numbers, which hasn't been answered. And that is, can we get rid of the n to the epsilon? Is the right result here not a question about dimension, but rather a question about density? And we don't know. So I'll have time to mention that open problem, hopefully, in just a few minutes. Okay, so we've seen 3 different ways now in which a p-Cantor set and a q-Cantor set are independent. So no mutual structure is possible. We talked about intersections, and now we've talked about sum sets. I want to tell you about how all of these generalize. There's actually 5 ways in which all of the statements I've given you so far generalize. So we just go through these really quick. P and Q, which were distinct primes, can change into R and S, where log R over log S is irrational. That's not a very big change. The sets A intersect B and A plus B, so intersections and sum sets, can change to A intersect an affine transformation of B and A plus an affine transformation of B. So if you're a number theorist, this might break your heart a little bit. At least it breaks my number theorist heart a little bit, because what this tells me is that A intersect B, having some quality that I've talked about today, somehow is not a number theoretic fact. Somehow A intersect B being small, or saying there aren't many coincidences there, it's still true. It's equally as true when we do A intersect an affine transformation of B. To me, this is much more of a geometric thing. And the way the proof goes here, in the back of my mind, I have, instead of intersections and sum sets, I have projections and fibers of projections, so a very much more geometric flavor. So anyways, that's another generalization here that can be worked in. The sets A and B can actually be replaced by subsets of A and B, and you have to work a little bit to get the formulation of the theorems right, but that's also possible. P-Cantor and Q-Cantor, these words, can change to times P invariant and times Q invariant. Times P invariant, times Q invariant are structures that are more general than P-Cantor and Q-Cantor. And I'm going to tell you about that in just a minute, because I think that I want to try and sell that here. I want to try and get everyone interested in this, because I think it's new and interesting. And cardinality can be replaced by a discrete Hausdorff content. So again, sorry to break your heart, number theorists, but going back to something more geometric of flavor here, and talking instead about cardinality, we can talk about discrete Hausdorff content. This is again something I'd like to try and sell to maybe other people who are interested in moving beyond measuring sizes in terms of cardinalities, but in getting a more geometric notion in the integers. Okay, let me tell you what P invariants and times Q invariants are, because this is, again, something maybe not many people are familiar with, and something that all of our results hold for this more general type of invariance. So to do that, I'm going to tell you about 2 different maps, the left map and the right map. This is a very simple map. The left map deletes the leftmost digit when you write a number in base P. And the right map deletes the rightmost digit when you write a number in base P. So really the right map is a divide by P and floor, and the left map is a subtraction. And then a set is times P invariant if it's invariant under both the left map and the right map. So a P-Cantor set is times P invariant, because a P-Cantor set just tells you which digits are allowed to appear And that's clearly invariant if I start deleting digits, right? If I take a word that only has some restricted number of digits and I delete letters, of course, the resulting words that appear still only have those letters. So p-Cantor sets are times p invariant. But then there are a bunch of times p invariant sets which are not p-Cantor sets. So for example, the set of powers of 2, which appeared in that conjecture of Erdős, is a times 2 invariant set. But it's not obviously not a 2-Cantor set. And then you can get fancy with it. So let me not, this has nothing to do with the rest of my talk. So I'm going to skip it for the sake of time. Right, so I wanted to try and sell somebody, at least one convert here, maybe on the idea that this discrete Hausdorff content could be useful. So if you don't know what Hausdorff content is or Hausdorff dimension, then I'm not sure that the 30 seconds on this slide will help very much, but this is the way you can define a discrete Hausdorff content for a compact set in R. And I'm thinking in my head that X is a finite subset of N. You just cover it with intervals the same way that you would, as usual, except that there's a lower bound on the diameter of those intervals. And then here is a more general version of a theorem which I told you about previously regarding sum sets. And again, I'm running out of time and I really wanted to tell you about some of these cool open problems which I want to invite everyone to work on. What I want to emphasize here in this theorem is that we have the Hausdorff content of the sum set being large. How large? Well, it has something to do with the Hausdorff content of the product set A prime times B prime. And somehow this is better than measuring cardinality. And I don't have time to say why. Okay, but if there are questions. Okay, right. I should say that this is a little bit of context. And this context is a couple of conjectures of Furstenberg in the 60s. Furstenberg conjectured that these types of inequalities that I've been talking about for sum sets and intersections of fractal subsets should hold. And in fact, in a remarkable 10 years of papers, these conjectures have been verified. So a lot of really amazing work went into verifying these conjectures of Furstenberg, and our work would not exist were it not for this sequence of results here. So I can't emphasize enough that behind the scenes in our work is well, I'm going to call out Schmerken mainly here. Schmerken's work in 2017 verifying this second inequality. And if you have two fractal subsets, one of which is structured with respect to P and the other is structured with respect to Q, their intersection is small. So this is Schmerken's theorem, and we use it by taking a subset of the natural numbers and scaling it down and understanding what happens as we scale it down to the real numbers. Lots of things can go wrong there. I'm sweeping a ton of stuff under the rug, but that's basically the idea. Okay, I'm out of time, but I'll just stop by leaving the slides right here. There are two open problems. The first two I kind of hinted at during the talk. And I'm going to choose one. I'm going to choose one, and I'm going to choose number 5 because I feel like maybe I'll reach out to somebody who wasn't really digging the talk so far. So we take the set of squares, and we take a p-Cantor set A, and we ask if we add the set of squares to this p-Cantor set, do we get to the sort of expected size? Expected size in this case is the size that would say, or these two sets are additively combinatorially independent. And the same thing with the intersections too. For example, are the set of squares and a p-Cantor set, are these disjoint? Are they transverse? Are they independent somehow? We don't know, and I think it's very interesting to ask questions of this form. This last question is of that form, and there's some recent work of Maynard that kind of says that maybe in some cases yes, but it's very difficult and very interesting. Thank you all very much for your attention. Sorry to run over.
Great, thank you so much, Daniel. Wonderful talk. I don't know. Oh, somebody raised their hand. I'm not sure whether raising your hand gains you access to verbal communication, but I don't see questions in the chat or Q&A. So I don't know.
Let's see.
Technicians behind the scenes can figure out whether raising a hand will get you access.
I see Sohail has raised his hand.
Yeah.
Yeah,
Yes.
now he can speak also.
Thank
Okay.
you.
Go ahead.
I noticed like 4 or 5 slides ago when you were mentioning those two conjectures about the dimension of A intersect B and the dimension of A plus B. I think one of the conjectures was that the dimension of A intersect B is smaller than or equal to 0, or, yeah, right here, dimension of X plus dimension of Y. I'm a bit confused because wouldn't the dimension of the intersection be smaller than either the dimension of X or the dimension of Y?
Yeah, this is a typo.
Oh. Okay.
Thanks. Yeah, so you've definitely found a typo here. So this should be dim x plus dim y minus 1.
Oh.
So I don't know if that answers your question or resolves your confusion, but thank you for pointing that out. Indeed, this is a typo here. This should be dim x plus dim y minus 1. One way to understand what y minus 1 is that this is a sort of codimensions add kind of thing. So if two sets are in general position, we might expect their codimensions to add. And if you figure out what that means, push the numbers around, then that's the number that pops out, dim x plus dim y minus 1.
Yeah, that makes much more sense to me. Thank you.
Okay, that's good. Thank you very much.
We have one question in the Q&A, which appears to have been answered by the person who posed it, which is interesting material question. Yes. Okay. So we're good with that.
I can answer questions like that. Yeah, that's.
Actually, I had a comment, or I don't know, a comment or a question on the problem that you had about sums of squares and the.
Yes, this one I think number 5.
So it seems like can't you use a mean square result to say something about this? Because if you look at the number of representations of integers, say, so some of the from a sub n and the element and the square, you look at this in mean square, then you basically are pushed towards the diagonal situation because of divisor type estimates. X squared minus y squared equal to something non-zero, we get just n to be epsilon representations. So it seems like maybe this first claim, this
Sorry, Trevor, are you talking about problem 4 or problem 5?
Problem 5. Actually.
Problem 5. So yeah, I think maybe I don't understand exactly what pushing toward the diagonal means. I'm.
So you sort of get the diagonal contribution, and then the remainder you just get n to the epsilon times something depending on its n squared. So it's sort of, I mean, if you work with a set of integers and you add squares, then it's sort of possible to increase the exponential density of this set that you get by adding these things, by just using a quotient argument and counting solutions in square.
I don't know, honestly, to be honest. So this says an invitation, and so if you have ideas, I should pick your brain. Perhaps I'll email you.
That was actually mentioned in Jörg Buden's talk earlier today. So
I'm sorry?
That was actually mentioned in Jörg Buden's talk earlier today.
Oh.
Exactly this sort of expansion using squares. He was really talking about expansion using cubes. Anyway, good. So we've got the same Q&A. So if there are no more questions for Daniel, we should thank him morally and maybe even with sound at some point. But,
yeah, thanks everyone.
Then we're wrapped up for this session, and we have a half-hour break at this point. I think Mel nodded briefly.